Good morning and good afternoon to everyone. So yes, my name is Aurélie Moll. I'm a strategic industry manager for CCUS, working for SIC in Germany. And today it's a pleasure for me to give you an overview about the CCUS market and the continuous monitoring system for the value chain. So first, I will introduce shortly my company, SIC. Then we will have a look on the decarbonization of the industry and the role of CCUS. After that, I will give you an overview about the CCUS market trend. I will also explain what CCUS is. And at least you will get an insight about our sensor solution for the complete CCUS value chain. So first about SIC. SIC is a German-based company with more than 70 years of experience in manufacturing sensor solutions for industrial applications. The company has more than 10,000 employees worldwide and 1.7 billion euros annually global sales. SIC offers more than 40,000 products that are used to increase work safety, to automate and optimize production processes, or to provide information for the environmental protection. In addition, SIC invests around 200 million euros annually in research and development. So this makes SIC one of the most innovative companies on the global sensor market. Our activities are organized in 3 segments: factory, logistic, and process automation, which cover all industries where sensor intelligence is needed. Especially within the process automation, for example, building materials, petrochemical, power, maritime, or waste to energy, all these industries are CO2 emitters and will therefore need CCUS to comply with the decarbonization target. With our wide product portfolio, we can solve nearly every industrial applications when it comes to presence detection, industrial safety, identification, or gas analysis and flow metering. So now we will see what is the role of CCUS within the decarbonization strategy. The human activities are increasingly influencing the climate, especially by using fossil fuels. This increases the amount of greenhouse gases and consequently the global warming. Mitigating the climate change is one of the most important challenges of this century, and it requires a massive reduction in greenhouse gas emissions. The concentration of CO2 in the atmosphere is 40% higher today than at the beginning of the industrialization. On the left-hand side, you can see the significant increase of annual CO2 emission from fossil fuels and cement production. And the second diagram shows the evolution of the CO2 emissions by sector since 1990. The main increasing sectors are the electricity and heat production, the transport, and manufacturing and production construction sector. The Paris Agreement in 2015 pushes forward the decarbonization of the industry. Its goal is to limit the global warming to 1.5 degrees Celsius compared to pre-industrial levels. As part of the energy transition, some decarbonization measures are foreseen in areas where CO2 is most emitted. But why is CCUS a key element to support the decarbonization strategy? The most international institutes and organizations all agree about the fact that net zero emission in 2050 is only achievable by using CCUS to offset remaining emissions. For example, the IPCC, Intergovernmental Panel on Climate Change, stated in its last report that the temperatures are expected to reach the 1.5 degree limit earlier than anticipated. That means that the decarbonization must accelerate. They also stated that CCUS can compensate the residual CO2 emissions to reach the net zero, or better, to generate net negative CO2 emissions. In its last report, Net Zero by 2050, the International Energy Agency estimated the required CCUS capacity to reach the climate targets. Today, the existing CCUS capacity is about 40 million tons CO2 per year, captured and sequestrated. The needed CCUS capacity until 2030 is estimated to 1.7 gigatons CO2 per year and 7.6 gigaton CO2 per year in 2050. So this is a huge growth in the next decades. Another important driver to accelerate the deployment of CCUS in USA is the 45Q tax credit, which gives interesting amounts for each ton CO2 removed. There is also a budget proposal to increase this amount until 2026, $50 per ton for geological sequestration and $35 per ton for sequestration with EOR, enhanced oil recovery, or other qualified use. Here we see the different scenarios from the IPCC report on global warming. All the scenarios show the development of anthropogenic net CO2 emission, and that the pathway to limit the global warming to 1.5 degrees Celsius plan the use of carbon capture with a level of 100 to 1,000 gigaton CO2 until the end of the century. Yes, as said before, CCUS will be used to offset remaining emissions and also to achieve net negative emission. For example, with BECCS, bioenergy with removal of CO2. This is an extract from the IEA report, and it provides the estimation of the required CCUS capacity to reach the climate target shared by industry sectors. Here we see that the main sectors where CCUS will be needed are the fuel supply with hydrogen production and biofuels, industry with the combustion processes and the production processes, and there is as well a new application for CCUS, which will grow in the next year, the direct air capture, where the CO2 is directly removed from the atmosphere. Now we will have a look on the CCUS market trend. This map comes from the last report published by the Global CCS Institute. It shows the current commercial CCS projects worldwide, in red in operation and construction, and in blue under development. Today, there are 135 CCS facilities worldwide, and 71 of them were added in 2021. This shows again the huge growth we had last year. We can also clearly identify the focus regions where the CCUS market is developing fast: North America, especially in USA, and the north of Europe with Norway, Netherlands, or UK. And the concentration of CCUS projects is mainly linked with the oil production regions, where the CO2 is used for EOR, or where depleted oil and gas fields are available for the geological sequestration. Industrial areas are also interesting for the development of CCUS. In fact, to enhance the development of CCUS in industrial area, so-called hubs or clusters are created. That means that different companies in an industrial area are collecting their CO2 to have a common transfer for utilization or storage. And this kind of network brings some advantages. like the proximity of industrial emitters, the common use of existing infrastructure, for example, pipelines, the construction of new common infrastructure. So at least this leads to cost optimization of CCUS projects. We have here a good example of a CCUS network with the number 7, Wabash Carbon Safe, where different sources of CO2 can be linked to the transport and storage system. We have here a coal-fired power plant, a natural gas power plant, chemical and petrochemical productions, cement plant, and waste incineration. The captured CO2 will be permanently sequestrated in a commercial scale geological storage. So regarding the market trends in North America, more than 40 facilities were added to the Global CCS Institute database last year. Also last year, the US rejoined the Paris Agreement. The US Energy Act of 2020 authorized more than $6 billion for CCS R&D and demonstration. There are also major bills introduced in the US Congress to augment the 45Q tax credits. Then we see in Canada that there are also propositions for tax credit for CCS projects, and also to include the use of CCS in clean fuel standards to generate credits. We also see that biorefinery network and low carbon LNG with CCS are emerging. So it happens a lot in North America regarding CCUS today. So, but what is carbon capture, utilization, and storage? This is an overview of the CCUS value chain. First, the CO2 is captured from industrial processes like cement production, waste to energy, power plants, or refineries. It can also be separated from the natural gas or hydrogen production to produce blue hydrogen. And it can be directly captured from the air. The captured CO2 is then purified and compressed for the transport that can be done by pipeline, ships, or trucks. And there are two possible ways for this captured CO2. First, with a permanent geological sequestration deep underground, onshore or offshore, or for enhanced oil recovery, where the injected CO2 allows an increase of the oil and gas production. And the second way is the utilization of CO2 for direct industrial use or after chemical conversion as a feedstock for the industry, for example, methanol or synthetic fuels. There are three main processes to capture the CO2. The pre-combustion process used, for example, for the hydrogen production with steam methane reformer. The post-combustion process that can be seen as a part of the flue gas treatment and can be retrofitted to each industrial plant. And the oxy-fuel combustion process, which involves pure oxygen instead of air and provide a nearly pure CO2 after condensation of the water. There is a further carbon separation process specific for the cement industry, where the unavoidable CO2 coming from the limestone is directly separated. Here you can see the example of the Lelac pilot project in Belgium. Approximately half of the CO2 emissions from cement are process-related and come from the limestone. The limestone releases the CO2 during the calcination process. So this process offers a way to directly capture this unavoidable gas stream as almost pure CO2. This is an overview of the main utilizations of CO2, the main possibilities. The first one, the most important, is after chemical conversion to produce polymers and with the use of hydrogen to produce fuels, chemicals, and commodities. As said before, methanol is, for example, an interesting feedstock for the chemical industry, and synthetic gas can be used to produce kerosene. There is a mineralization process to produce construction material and carbonates based on CO2. There are several direct utilization for food and beverage or as industrial fluid. And CO2 can also be used with a biological conversion, for example, in greenhouses to support the growth of tomatoes. Regarding the sequestration of CO2, you can see here the different possibilities with the injection deep underground, onshore or offshore, for example, in saline formations, in unmineable coal seams, for enhanced oil recovery, or in depleted oil and gas reservoirs. So now I will give you an insight of our sensor solution for the CCUS value chain. So previously we have seen the complete CCUS value chain. It includes different industries, processes, and applications with several interconnection and interfaces. So to control and optimize the processes, continuous gas analyzers and flow meter are essential. You see here some example of measuring points for gas and flow at different interfaces, in red for gas analyzer, in blue for flow meter. So nearly everywhere you need analyzer systems. With our existing product portfolio, we can propose solutions for most applications within the CCUS value chain. The continuous gas analyzers are used to measure the CO2 concentration, to control the efficiency of the capture process, and to calculate the exact amount of the removed CO2. The gas analyzers are also important for quality control to measure the concentration in other components that are considered as impurities and can have an influence on the further steps within the value chain, for example, corrosion. For these applications, we provide different type of technologies depending on the application and on the measuring task. For example, in situ analyzer, when only CO2 is required, or hot-wet extractive analyzer for simultaneous multi-component analysis up to 12 components, or cold-dry extractive analyzer, also for multi-component analysis, but when no water-soluble components are required. Then the CO2 flow measurement is also necessary at each transfer point to control the quantity and the volumes of captured CO2 or sequestrated. For this, we are using our ultrasonic flow meter, FlowSig 600, which has a long experience with custody transfer for natural gas and can be similarly applied for CO2. SIG also provide turnkey measuring systems like metering skids or analyzer shelters. Here we propose a flexible solution with the integration of our instruments as well as third-party products or instruments if required. Carbon capture is not completely new, and some pilots have been realized more than 10 years ago. We participated with our gas analyzer to the first 2 pilots with oxy-fuel combustion process at coal-fired power plants. We delivered a total of 8 multi-component gas analyzers, 6 hot-wet extractive in red, and 2 cold-dry extractive in blue. They were used to measure the CO2 concentration and other components at multiple points within the process. After specific calibration, due to the high CO2 concentration and existing cross interferences, the analyzer were able to produce reliable results. So you can see on the right-hand side some example of measuring ranges we have provided, and especially the CO2 up to 200 or 90 or 100% in volume. A third project was done at a steam methane reformer for hydrogen production. Here again with a multi-component hot-wet extractive analyzer and a measuring range of CO2 0 to 100% in volume. This is here another application with the LELAC project. We participated with our analyzer to the first pilot. So as seen before, here the process-related CO2 from the cement production is separated by indirect heating of the limestone. And in this project, 3 components were important for monitoring and optimizing the process. First, CO and O2 for the control of the combustion, which is a standard application with in situ analyzer. And then the CO2 to monitor the efficiency of the carbon capture process. And this was as well realized with an in situ analyzer. This analyzer for CO2 provides fast and accurate measurement with CO2 concentration up to 100% in volume. Along the CCUS value chain, flow metering is essential to control the exact quantity of carbon dioxide transferred for storage or utilization. It will become more and more important when it comes to CCUS networks, where several companies are involved, so several interfaces. It is important to invoice the CO2, to report the amount of removed CO2, and also to claim for tax and credits. Since over 10 years, we are using our ultrasonic flow meter for the metering of CO2 transport. Again, the FlowSig 600, which is well known for natural gas custody transfer, is also perfectly suitable for CO2 up to 100% in volume, and for gas and dense phase. It is applicable for pipeline size between 3 and 24 inch and pressure up to 250 bar. And the measure is accurate as well, with plus minus 0.5 to 1%. So it is similar to the performance for natural gas. But CO2 is not so easy to measure as natural gas. In fact, CO2 has an attenuating effect on the ultrasonic signals, and the speed of sound in carbon dioxide varies strongly depending on the pressure, temperature, or gas phase. So that's why the flow meter for CO2 applications has to be specifically adapted regarding the design parameters. Especially the probe frequency has to be adapted, and the presence of other gases is taken into account during calibrations. Considering all these parameters, SIC as an optimal solution with a high precision up to 100% of CO2. As an example, SIC supplies customized turnkey systems for CCUS. Here we see a metering skid with our flow meter, FlowSig 600 as the heart of the system. We have here also the integration of our analyzers as well as third-party instruments depending on the specification. And the data handling is also part of our solution. This is an example of a fully integrated analyzer shelter we provide. And here some metering skids, in this case for natural gas, but they look similar for CO2. So to conclude, we can say that in addition to the development of renewable energies, CCUS is a key element to achieve the high CO2 reduction targets. With CCUS, the CO2 emission of energy production from fossil sources can be significantly reduced. CCUS can also make a major contribution in CO2 intensive industries such as cement, metal and steel, as well as petrochemicals. And CCUS is also important for clean gas production, like blue hydrogen. Continuous measuring systems are required to control the efficiency of the processes, the quality of the gas, and to measure the flow of carbon dioxide within the CCUS value chain. The challenge for the continuous measuring systems is the diversity of processes and the different operating conditions along this CCUS value chain. But there are currently measuring systems or measuring devices that can be used for CCUS with less or no adjustments. Finally, the design and the development for measuring systems will have to be compliant to future regulations and performance requirements, for example, for fiscal measurement. But for all the emitted industries, SIC already provides solutions for almost all measuring applications and will also support the CCUS development with suitable gas analyzers and flow meters. Don't hesitate to visit our website and download our dedicated brochures to learn more about our solutions for CCUS. I thank you very much for your attention, and now it is time for question and discussion. And here you can see our contact, especially Mark Kennedy, who is your contact in the USA. Thank you.
Thank you. Thank you